Okay, all right. So okay, I'll just going to continue with sort of the phase diagram that I introduced before, and really, so now I'm going to talk start talking about the superconducting state that we observe here, and really just to give you some just sort of experimental signatures that one observes when one looks in closer detail to the superconducting states here. So of course, first of all, like what are the signatures of superconductivity? Of course, this is just zero resistance, right? So basically, when we measure resistance as a function of temperature, we observe a clear sort of transition to a zero resistance state, and really zero means zero. Usually this sort of zero resistance state occurs at around 1 Kelvin Tc. So this is not a terribly high Tc, but I will explain later that this actually is still special in such a low density system. So Tc is around 1 Kelvin. Then of course the other signatures of superconductivity is Meissner effect, so that you can kill the superconductivity with an in-plane magnetic field, sorry, out-of-plane magnetic field. And this is basically seen here. So this is the critical magnetic field. So this is the magnetic field you need to apply to completely kill the superconducting state and get a resistive state again. And this is plotted as a function of temperature. Sorry, this is not Tc, this is just T. And the critical magnetic field is a function of temperature, scales as you would expect from a Ginzburg-Landau theory, with a critical magnetic field of around 100 millitesla. So this is also all consistent between all of the devices. And of course, looking at the Ginzburg-Landau theory, we can also see that coherence length is here in this formula, and we can also deduce the coherence length from this formula. And the coherence length is in the order of 50 nanometers. So in principle, you can start comparing the coherence length to the Moret lattice spacing. So this is really around 3 lattice constants of the Moret. Then, of course, the other thing is we measure nonlinear conductance. So this is basically typical measurements that we do is measure dV, di. So basically, nonlinear conductance is a function of a DC current. So we apply a certain current across the device, and what we can see here is really that it has these nonlinear features, where we basically can define a critical current here, above which the superconductivity again vanishes and the device turns resistive again. And the critical current is usually in the orders of 10 to 100 nanoamps, which is of course related to the specific sample geometry and so on. But this is all pretty much consistent across the devices. And furthermore, what we can also do is we can try to look at sort of the dependence here of the transition to a normal state, and we can show that it's actually a steeper transition than power to the I to the third, and this is really indicative of a two-dimensional superconductor. So this is indicative of a Brzezinski-Kostelis-Towns transition in typical three-dimensional metals. This is not what you would expect to see. And all of these features combined, so the three features which I showed you before, in the beginning of that field would still not silence critics. So a lot of people would still say that, okay, so these features can be explained by other means. So for example, I mean, yesterday Philip was showing you sort of topological states in the twisted Bilayer graphene and so on. So some people might say that the zero resistance come from topological states, for example. Right, so that would really those three sort of evidences would not be completely enough. But what is really hard to argue against is also the Fraunhofer interference patterns that people observe. And Fraunhofer interference patterns in these devices occur typically because some random Josephson junctions were formed. So because the devices are still somewhat disordered, very often you find superconducting regions which are interrupted by a weak link between one another, and if you measure transport in these, you basically effectively measure a Josephson junction. And these Fraunhofer interference patterns are basically a direct consequence of the coherent properties of the macroscopic superconducting state. So those are really properties which are otherwise hard to mimic by any other sort of mechanism that could be given rise to. So by now, I think nobody in the field doubts that it's really superconductivity which is observed. And later on, I will also show you that one can produce gate-defined, so basically engineered Josephson junctions, and one can turn on and off these Fraunhofer interference patterns. One thing which, of course, immediately in the beginning, basically in Pablo's first paper, was raising a big question is what is the nature of the superconductivity? And early on, there were immediately a lot of sort of attempts to say that this is really an unconventional superconducting state, and indeed, there are really a lot of very unconventional properties of the superconductor. So in Pablo's first paper, they plotted out this Uemura plot where they compared the critical temperature of the superconductor to the Fermi temperature of the electrons. And the Fermi temperature is really proportional, or it's basically proportional to the size of your Fermi surface. And of course, because twisted bilayer graphene is a semi-metal, has a very small Fermi surface, Fermi temperature is extremely small. And what people do in the strongly correlated community, they usually like to compare TC to TF. And usually one measure of how strong the superconductor is coupled is defined by this TC versus TF ratio. And this is basically plotted over here in this inset. So TC over TF is a function of for different material species. And so if you look at typically the normal superconductors, traditional DCS type superconductors such as aluminum, niobium, and so on, then typically these materials have extremely high TF. So those are usually good metals. So TF is really high, and TC is not particularly high. So maybe 10 Kelvin or in that order. So, but if you compare the ratio TC over TF for these materials is extremely small. It's much, much smaller than, for example, for high temperature superconductors, which are usually not such high density systems, but they have still much higher TCs. So the interesting thing is here, now if we try to put graphene on the map here, this is done here in this graph by Pablo. One finds that actually the TC over TF ratio in magic and graphene is much, much higher than in most traditional superconductors. And it's actually even higher than, for example, high temperature superconductors like heavy fermion systems or high TC cuprate superconductors and so on. So from this analogy, one can already try to put the superconducting state in graphene closer to an analogy to really these unconventional superconductors like high TC systems, etc., than to other BCS-like superconductors. And so another way of thinking about this graph is, so this is what we plotted out. We plotted out different superconductors based on their thickness. So how thick can you make a superconductor? And also how what is the carrier density in the superconductor? And as you can see, so graphene is the most two-dimensional system you can make. So this is really the thinnest superconductor you can produce. And at the same time, it's also orders of magnitude lower carrier density. So as you can see, so magic and graphene is here. It has a carrier density in the orders of 10 to the 11 electrons per centimeter squared. And if you look at, for example, aluminum, which is kind of our most sort of famous widely used superconductor, it has a carrier density almost 6 orders of magnitude larger. So really, it's really surprising that it's such a low density electron system. One can still get a sizable TC of 1 to 5 Kelvin, right? So I mean, I think in the best case, we found a superconductor TC of 5 Kelvin. Okay, and then of course, what was immediately also raised by Pablo is also the phase diagram, the way we sort of plotted. So here's, for example, a phase diagram of the cuprates. So cuprates are a priori also in the sort of zero-doped case. Those are Mott insulators with antiferromagnetic water. And if you dope the crystals basically in the electron of the whole side, you also kill the Mott insulating phase, and you recover dome-shaped superconducting phases from this. And in principle, if if we pick out sort of the phase diagram of graphene that we showed before, so this is, for example, one of the zoom-ins on one of the half-doped states. Very often we get a very similar picture. And at one of the integer fillings, we have one of those mod insulating states, and depending on doping levels, so if we dope in and out of the correlated insulator, we end up having these dome-shaped superconducting states. So also here there is a little bit of analogy that you can in principle paint towards corporate superconductors. Now that being said, I really want to emphasize that this is all hand-wavy arguments at this point. I think still the mechanism of superconductivity in twisted bilayer graphene is not understood. But of course, I think there will be a lot of work going on in the next couple of years to really try to address this sort of question. And so one thing I want to mention is that there has been already some sort of progress in addressing these questions. So, for example, of course, one of the questions is what is the symmetry of the superconducting state? Is it a S-wave superconductor like all the BCS type superconductors, or maybe is it something more exotic? For example, like a D-wave superconductor, like with a nodal pairing symmetry, like we know from the cuprates or other unconventional superconductors. And so I think the first work to really address this question seriously, to really try to get some quantitative evidence, came here from the Yazdani group here at Princeton. So they, of course, are famous for these very beautiful spectroscopy maps as a function of filling, where they basically do spectroscopy tunneling experiments in the twisted bilayer graphene. And what they found is basically that they can zoom in on one of those superconducting pockets that they can identify in the spectroscopy maps, and they can really do careful tunneling spectra and extract sort of the shape of this tunneling spectra in the devices. Similar work was also done by the Nashpergi group, who also did similar experiments on magic angle twisted trilayer graphene. But in principle, probably a very similar superconducting state that they observed. So what's interesting here is that really they observe shape of the superconducting dome, which is this V shape. And this V-shaped dome typically is a direct indication that the pairing symmetry could be nodal. Okay, so in principle, if you have an S-wave superconductor, as you see, so there's a continuous gap in all the k vector directions. So it's usually a very sharp and hard gap, and you usually should observe very sharp non-V-shaped like features, but more like U-shaped like features.
So it should be nodal point, or does it tell you if it's a maybe nodal line or?
Yeah, exactly. So exactly. So you from these spectra, you cannot tell if it's P wave or D wave. You can only tell that it's nodal.
But yeah, cannot tell you whether the nodal is a point node or a line node.
Yeah. Okay. That would be difficult probably.
So 2 dimension probably only have points.
Yeah.
But I think it can't be. It's possible to get this mobility work Fermi surfaces.
Yeah, but 2 dimension, your Fermi surface is a line. And you want to get it in some way, as you see, the gap is saying manifold will be smaller than the dimension of Fermi surface. It will be points. Yeah, that's my understanding.
But so what I also want to say is that, so of course, look, I mean, of course, S-wave superconductors should have really sharp boundaries here. But of course, there's still disorder, there's still temperature, there's a lot of broadening that can affect it. So in principle, here is like an attempt to plot sort of fit it with S-wave superconductivity too. And of course, they can get similar shapes like this, but still the best fit what they got is fits best with a nodal gap. And I think it's a point gap like what is shown here. But so in principle, what this already tells you that it's kind of a fine distinguishment. It's probably hard to interpret too many details into that and tell whether it's D wave or P wave or P plus IP or something like that. So it tells you that really it behaves different than S wave and more closer to D wave.
And it also makes experiment on double bilayer graphene as well.
Sorry?
On double bilayer graphene.
No, this double bilayer graphene is not superconducting.
Oh, it doesn't.
It's not superconducting, but on trilayer. But so, okay, so this is, I mean, this is from what I know, this is sort of really the first experiments that really try to address some pairing symmetry to this question, and I think this is really the first step towards really understanding of a pairing mechanism. And in this line, we also did some experiments to also address this. And what we did is we tried to measure thermal connectivity in the superconducting state. And thermal connectivity also is a quantity which can allow you to distinguish whether something is S wave or D wave superconductivity. Because again, as I mentioned before, so sort of if a gap is really continuous in all the directions, thermal connectivity is really quenched exponentially in a superconducting state like that. But whereas if you have a normal superconductivity, there's always thermal connectivity along the nodes that can be non-zero. So it really, those two quantities should behave very differently. And so what we did is we basically use some volumetric measurements. So we basically, what we do is we measure transport in a typical twisted Bilayer graphene device, but we try to heat the electrons by sending laser light on it. And the laser light, what it does, it usually excites some electrons, so it creates these electron hole pairs. But these electron hole pairs very quickly thermalize. And what you end up with is you just basically end up with a temperature gradient in the flat band, which is slightly higher than your bath. And what it means is if you wait long enough, so once you heated up your flat band electrons, once you wait long enough, thermal conductivity will just release the heat into the environment. And this is something which you can basically deduce information of thermal conductivity from. And so what you need here only is you need you need to define the temperature of the flat band here. So once you send in some sort of power of the light, and you can read out the temperature of your graphene electrons, then you basically can do this experiment. So what we did to extract the temperature of the electrons here, we just really looked at the IC of the superconductor. So and this is really showed here. So this is the temperature. This is the VDI as a function of temperature and current. So this is basically the same measurement I showed you before in these nonlinear conductance measurements. And really these blue areas here, this is our superconducting region here. And again, if we bias above that region, it becomes non-superconducting. And so from these peaks here, which mark the transition from the superconducting non-superconducting state, these peaks are really sensitive on temperature. So you see, if we increase the temperature, we basically quench the superconductor, and we can really use these lines as a thermometry. And at the same time, what we can also do, we can repeat the same type of measurements, but now with instead of increasing the temperature, but instead of function of the laser light with which we heat it with. So this is PL. This is the function of PL. This is a function of photons that we sent into the system. And what you can already see is that those two graphs look almost identical. So in principle, we can really relate the electronic temperature to the laser power that we sent in. And we can really extract from these thermometry curves, we can really extract some sort of thermometry, and we can define the electronic temperature really accurately. And so what we were able to do is we were able really to study the volumetric effect in the superconducting state. So again, we were looking at how the superconducting state responds to the heating. And from the temperature increase in the superconducting state as a function of laser light that we pump into that, we can directly deduce the thermal conductivity by this steady state formula. So thermal conductivity is nothing else than the power that you pump in divided by the temperature increase of the system. And so what we found is here, again, by doing so, we were able to plot the thermal conductivity as a function of temperature. And we were able, so those are these points here that we extract from our measurements. As you can see, what we found is that the thermal conductivity in these measurements is really behaving closer to what you expect from a nodal superconductor than from an isotropic X-ray gap. And really, and the difference here is really the following. So for isotropic superconducting gap, like an S1 superconductor, we expect really exponential activated thermal conductivity. So thermal conductivity states really 0 up to certain high temperatures. And in our case, really, it's not exponential. It's really more like a power law behavior, like what you would expect from heating S-wave, D-wave superconductor, for example. So I think that this is also extra evidence that based on the initial work by the tunneling spectroscopy, this is another piece of evidence that indeed something in the superconducting state behaves closer, is better explained by nodal gaps than by S-wave gaps. Yeah.
Why at the low temperature it's off? If you look at your data insets, right?
This here?
Yes.
Okay.
It seems that the points starting really off at lower temperature.
Here, 1 point, please.
Yeah, yeah. Of course,
1 point.
the question is that
Yeah, okay, so this is a millikelvin temperature, so this is 35 millikelvin. So it's really at 35 millikelvin, maybe the temperature of the fridge is not exactly the electronic temperature. So that's why the error bar here is also so much bigger. Okay, so this is 35 millikelvin is really low temperature. So then one needs to calibrate your electron back very carefully.
Professor?
Yeah.
Have you tried to change the confinement? I was just wondering if this effect is like because of some sort of fluctuations. Because you go lower in temperature, the effects of quantum mechanics become more dominant. And if you, for example, I don't know like how small it
As far as I'm concerned, everything is quantum mechanics here.
well, in some sense, yes. So my point is other fluctuations make any difference for your kind of systems? Lower temperatures.
So
I mean like zero oscillations.
yeah, so zero oscillations, I would not expect them to play a role here. But okay, so what we need to be careful. Okay, so what we need to be careful here for are basically is Johnson noise. That's something which we need to be careful with. There's Johnson noise in the system. There are thermal fluctuations in the system. This is all we need to be careful with. And of course, whenever we shine light on it, of course, there's also within sort of this process, right? Within the process of exciting electron hole pairs and then relaxing down, there's of course also we need to be a little bit careful. There might be extra thermal conductivity through these higher bands, right? So in principle, there's definitely things one needs to be careful about. But we estimated in the paper. We think that so this increase of thermal conductivity can still not be explained by these fluctuations.
Wouldn't it be that this non-zero thermal conductivity at low temperatures can be explained by some other kind of excitations, maybe neutral ones, and with S-wave conductivity?
Yeah. So look, I mean, if you can specify what it can be, we can try to think about it. I mean, so you have to tell me what type of excitation that should be, then we can start thinking about it. Because I'm not sure what kind of neutral excitation would you propose?
There's some spin waves on top of this Bilayer Graphene state.
Okay, yeah. So we'll wait then. We'll wait for the theory paper to come out then. Yeah. Yeah.
So this is above gap excitation with the laser, right?
Yeah, that's right.
So very naive question. How do you know that you don't break the superconductivity with the laser? Because
yeah, so okay, so this again, so this is this type of experiments have been done before. So in principle, you have to basically look at sort of all the gaps and all the possible excitations that you can produce with a laser. So in graphene, typically, I mean, specifically if you use like telecom light, which is high energetic, you usually have certain excitation pathways which are well known. So if you would, for example, try to break a Cooper pair, you would have to excite somewhere. I mean, you would have to find that excitation and momentum space which allows you to perform this excitation, to conserve momentum, etc. So
So you're saying
yeah.
that these are different excitations than Cooper's first. You still
Yeah,
preserve the
exactly. So
Cooper's first, but you
right,
somehow-
exactly. So I think if we want to break Cooper pairs, then typically, in my understanding, you need to use terahertz light or something like that, which is not momentum conserving, and which is also lower energetic
Yeah.
light that you need to make these excitations.
You can still start much above.
Yeah. So here is the question: whether you would find above, if you go from the flat band here,
Yeah.
in that sort of, with this sort of vector here, right?
Yeah.
Would you find a state in which you can excite this? And we concluded that there is no excitation like that,
Yeah,
because you excite somewhere in the middle of the Fermi surface. There's no, like, you don't have a Fermi, you don't have a free electron state there.
On the other hand, the flat band has some very high density of states, right? So excitation from flat bands in general
Yeah.
are very efficient.
Yeah, but you have to make sure that in momentum space it's also conserved. I mean, the reason these excitations are straight because they're momentum conserved.
it's
Right? Yeah.
Related to the fluctuations question, where is the critical temperature on your thermal conductivity?
Here, critical temperature.
Next slide. Yeah, the critical temperature. On
Oh,
the
it's so this is around here. This is probably at what one here.
I see. So
Yeah.
that's why you don't expect autoground fluctuations to multiply.
Yeah.
I might miss someone. Is the sample broken, or is this suspending from the substrate?
No, it's on the substrate.
It's on the substrate.
Yeah.
So how can we screw the
Yeah.
conduction between the?
So okay, so there's been a ton of literature sort of studying light matter interactions in graphene, and indeed this is one of the questions that arises all the time. What is the thermal conductivity? And so basically the thermal conductivity pathway that we paint here is sort of what works also for single layer graphene really well. So only there is basically a photoexcitation process which happens on a scale of around 100 femtoseconds. Sorry, no, this happens on a scale of a few femtoseconds. This is a really fast process. Okay. Then the process of these electrons relaxing down and forming like a temperature distribution is around 100 femtosecond, and then the cooling into the environment is around 1 picosecond process. And so basically, if you assume a process of lattice cooling between, and so this is all electrons. So far we have not even looked at phonons. So phonon processes are much slower. They happen on like 10 or 100 picosecond scales. And basically, after this fast process is done, then only something happens with the lattice. But usually this is, in graphene, this is a process which can be almost ignored. So really electron interactions are fast process and electron phonon between graphene electrons and graphene phonons. And then only way later, phonons between graphene and HBN, etc., start to play a role. So, but these processes are well studied for single layer graphene. You can really take this over from that field.
So next question is about the calculation for the power.
Yeah.
So is the power you indicate here is measured somewhere, or is just the line power?
So okay, so exactly. So the same story is for single layer graphene. So we know that for single layer graphene, 2.3% of all the incident light is absorbed. So for 2 layers, it's 4.6%. So this is all very well studied. And for twisted bilayer graphene, we make the assumption that because our wavelength of incident light is so much bigger than the moire, that the moire is really just a small perturbation. So we expect for twisted bilayer also 4.6% of light absorption. So this is how it's calibrated.
So will this kind of calculation affect the fitting result for the nodal cap or the?
No. This would be just no. This actually this would not affect it exactly. That would be just like a prefactor. So yeah. So really, what's important here is sort of the line shape, right? Yeah. Okay, so then moving on. So basically, I'll talk now about Josephson junctions, and basically what we found really interesting when we observe phase diagrams like that is that really, if we look at the phase diagram, you find that there are really coexisting magnetic states and superconducting states, really just depending on the gate voltage that we apply to the device, right? So for example, here at a certain gate voltage, we have a superconducting state, and if we really just increase the carrier density, we can tune into a magnetic state, right? So in this really excited us, because in principle now you can really use gate-defined sort of geometries to make more complicated Josephson junctions, where you can tune the leads, for example, in the superconducting state, and you can use a local gate where we can tune the device, for example, to a magnetic state. Of course, when we started the study and really wanted to make magnetic Josephson junctions, we were not yet aware by the experiments that Ellie Zeldov did in our devices. We were not exactly aware how rich the domain structure is, right? Because if you really want to make a Josephson junction and make a Josephson junction in a device like that, you need to be a little bit lucky with the domain walls that you can trap in one of those non-superconducting regions. But anyway, so we started to do experiments before that, and really this is the device geometry which we came up with. And basically, this is a double-gated device. So it has a graphite bottom gate and it has a graphite top gate. But in the graphite top gate, we make a small line cut to really interrupt the gate. And so what you can do now by playing with the right gate voltages, etc., between top and bottom gate, you can really tune the carrier density in that region, in the center region, separately from the rest of the device. And you can really create a density profile like this. So this is density as a function of position, right? So along this trajectory. So you can really make a device where most of the device has a certain carrier density, but only inside this gated region of around 100 nanometers, you can make a different density configuration. And of course, the idea was that we can make a Josephson junction where we basically keep most of the device in this superconducting state, and only in the middle region we can tune it to any other correlated insulator state, and ideally into sort of a magnetic state. And this way we can create a magnetic Josephson. And there was, of course, similar work already done before by Pablo and Condensed group, who did also showed gate-defined junctions like that. And so this is sort of a typical data that we obtained. So this is basically DDBI, nonlinear conductance, again, as a function of NJ. And NJ is really just the density region in the middle. And the density regions on the leads, we keep them fixed in a superconducting state. And so really, depending on where we are on the NJ region, we can also take resistance measurements separately. So we can also know that, for example, in the center region here, the NJ is also superconducting. And then here in that region, NJ is just metallic. And here in that region, it's really in the correlated insulator state. And what we can do now is we can, for all the different positions here, we can try to take Fraunhofer patterns. So this is what we did. So here in the center region, this is really a region where we understand as an SSS. So it's really a homogeneous superconductor all across without any junction. We observed this typical diamond-shaped superconducting region. This is looks pretty much the same as we observe in a really clean non-gated device. So this is really consistent with a continuous superconductor. Then here in this region where the central region is normal, it's a normal metal, we start observing some Fraunhofer interference pattern. And really this Fraunhofer interference pattern, what's important is it's really symmetric along the current and magnetic field directions. And then in this region where we tune the superconducting, the central region to close to the correlated insulator, where again, we expect some magnetism and so on, we start observing really well-pronounced Fraunhofer interference pattern. But as you can see, this Fraunhofer interference pattern looks very different than this one here. And in particular, it starts looking asymmetric with respect to the current and magnetic field direction. And so really, I want to highlight the differences here that we observed. So first of all, if you look at line cuts along this Fraunhofer interference pattern as a function of magnetic field, you can see that this Fraunhofer interference pattern really switches symmetries. So basically, it's whether you sweep the magnetic field up or down, it really is like if you switch plus and minus signs in that curve. And also, of course, you see some sort of phase shift. So these interference patterns, they don't line up on top of another, but there is some sort of phase shift. Moreover, of course, if we take also the line cut in this direction, so in the current direction, also in the current direction, these fields, these curves look very different, and they look completely asymmetric, depending on the sort of whether we applied a positive magnetic field before taking that measurement, or whether we applied a negative magnetic field before taking that measurement. And even more interesting, so you can see this effect. Really, when we took the Fraunhofer interference pattern as a function of only positive magnetic field, so we only swept the magnetic field in a positive direction, and then we took the same data, sweeping the Fraunhofer interference pattern in the negative direction. And you can see, so basically, if I take the bottom curve, rotate it and mirror it, it will fit on the top one. So there's really some sort of symmetry, folding between those two curves. And of course, there's also sizable phase shift from the zero interference. And of course, we can do all these sort of hysteretic measurements also for different magnetic fields, and we can see that really at around 800 millikelvin, there's almost no hysteresis between the Fraunhofer, and then it becomes much more pronounced. And really, we can also fit the size of this magnetic hysteresis with some sort of critical behavior. So okay, so this is already some sort of indication for us that okay, something is going on here, which is not explained by normal Josephson junctions, but it almost smells like some magnetism here, right? With all the hysteresis that is going on, and really, we, for example, we try to do some checks and balances to make sure that we're on the right track. So, for example, when we may measure the VDI at the first cool down of the sample, before applying any magnetic field, it always looked very symmetric. And only when we started applying magnetic field, so for example, here positive 500 millitesla, it started resembling this asymmetry. When we applied a negative magnetic field, it would flip the symmetry into the other direction. So okay, so what is going on here? So we of course try to an attempt to explain also theoretically what's going on here. And so basically we collaborated with a group, Katie Lau in Hong Kong. And we tried to really just to ask the question, what would be the simplest possible state that could potentially explain such a behavior? And the simplest possible state, again, it's not the only state that could explain it, but I think this is just the simplest possible state that could explain it, is, for example, one of those valley polarized states, which I showed you before in the Chern insulator session. So doing Green's function analysis on these devices, they were obtaining really similar behavior when they basically assumed S-wave superconductivity, and in the center, one of those valley polarized states, where really they could reproduce these interference, this hysteretic behavior, and they also could reproduce this sort of symmetry changing whether you sweep it up or down. The other indication that such a state could explain this is again in the orbital magnetization you can derive from such a state. So again, you can take the state and you can derive sort of the orbital magnetization the states produces just by the loop currents which exist in the system. And this orbital magnetization typically gives you some value in the orders of a few micro Bohr magnetron, so in the orders of 6 or 7 Bohr magnetron. And really, when we look at our experiments, so the phase shift we observe is usually consistent with that number. There's also these 10 up to 10 Bohr magnetron phase shift that we extract for this device. And last but not least, what's also observed for these orbital magnetic states, so there was, for example, a paper by Andrea Young 2 years ago where they actually showed that they can switch these orbital magnetic states by applying a current in different directions. So these orbital magnetic states really are special that you cannot not only switch them by applying a different magnetic field, but you can also switch them by driving the current in different directions. And this is really something which we also see in this device. So again, this asymmetry in the current direction that we observe is also explained by some sort of magnetization switching in the current direction. So one thing that we also realized in these devices is, of course, people always try to think of applications. So one thing we realized in these devices is that this asymmetric behavior of the DVDI characteristics as a function of current also has some nice applications, such as superconducting diode behavior. And really, this asymmetric behavior means that for certain current that where the device is superconducting in one direction, it is actually resistive in the other direction. So in principle, you can by sort of applying different values of current, which fit sort of in this window, you can basically turn on and off the current in one direction where it's really superconducting in the given direction, and then it's resistive in the other direction. So this is really also a nice application of this device. Okay, so how much time do I have? 20 minutes? Okay, all right. Okay, so last but not least, okay, so so far I covered all the phases. So, and last phase is of course the strange metal phase. And so really, let me just take the last 15 minutes to also cover that. And basically, the strange metal phase, as the name already says, you know, if a state is called strange, that just means we don't understand what actually is going on here, right? And so basically, the strange metal phase is one of, I mean, some people say it's a really big, one of the really big open mysteries in condensed metaphysics. But in principle, really, what's going on is it's a metallic state, which people observe in many correlated systems, which behaves very distinctly from what you would expect from Fermi liquid theory. Okay, and of course, it's a little tempting to draw analogies to sort of other systems like the cuprates or quantum lattice systems, iron chalcogenides. But what really, without sort of drawing too much analogies to twisted bilayer graphene here, what these materials have all in common is sort of a certain set of ingredients that we also indeed find in twisted bilayer graphene. And this set of ingredients is that there's in all these materials there's some sort of magnetism. So again, in the cuprates, it's antiferromagnetism. In the condensed lattices, is ferromagnetism and so on. There is very often based depending on doping or pressure, superconducting state that is close by. And all of these materials also show this strange metal behavior. And again, we don't know exactly what it is, but we know what the phenomenology of this strange metal behavior is. So again, what I'm saying about strange metal is only phenomenology. We don't really want to compare mechanisms or so. So in the phenomenology shows that this strange metal behavior has a linear resistance versus temperature. And again, this is in contrast to what you would expect from liquid theory, which sort of predicts T-square dependence. It also has a linear magnetoresistance. And if you look at the scattering rates in this material, the scattering rates are as fast as you can be. So the scattering rates are basically defined by the Heisenberg uncertainty principle, and they're basically limited by these flanking scattering rates. So in principle, strange metal is also a very bad metal. Usually it's a high resistance state, very strong scattering, even at the lowest temperatures. And again, flanking scattering rates are nothing unusual at high temperatures. So if you heat up any metal to high enough temperatures, you will always hit the flanking limit. At one point, there's enough scattering going on in the materials. What's unusual if you find the flanking scattering rates at like millikelvin temperatures. It's like really cryogenic temperatures where really not a lot of scattering events should be happening. Okay, so and really in twisted bilayer graphene, this story started developing really early on. So Pablo reported a strange metal behavior very early on in 2019. I think this paper came on archive. And what they saw is really similar observables that I showed you before. So they measured resistivity as a function of temperature, and then really for many decades in density, they observed these really linear temperature dependencies from around 1 Kelvin to 30 Kelvin. However, at the lowest temperatures, we're not able to really observe these the continuation of these linear curves, because at low temperatures, usually that's when we start developing correlated insulators, superconductivity. There's a lot of phase transitions which are going on at these low temperatures that obscure sort of this metallic behavior. And also Pablo back then, we also observed Planckian scattering rates. So basically, by measuring temperature-dependent Shubnikov de Haas oscillations, they were able to extract the effective mass and extract also the scattering rates of the electron. So that being said, back then, there was also immediately follow-up work by Andrea Young and Corey Dean, who basically measured a very similar data set, but they explained it with electron-phonon interaction. And they claim that really a lot of these linear temperature dependencies, they can be explained by electron-phonon interaction as well. So basically what we try to do now in our work, we try to sort of solve this mystery a little bit and define sort of a phase space where we can basically distinguish between something which can be explained by electron-phonon and something which maybe cannot be explained by electron-phonon. And so this brought me, the study was really interesting to me personally because I already worked in electron-phonon interaction with Philip. This was basically my first PhD paper where we looked at this problem from an electron-phonon interaction. So it was really good for me to come back to it. And indeed, a lot of those features which Andrea reported in this paper sounded very familiar. So this is typical data in single layer graphene. And really, indeed, as you can see, linear temperature dependencies in the high temperature limit are not so unusual. So if you look here, most of these curves become linear at around 100 Kelvin. So above 100 Kelvin, linear temperature dependence was nothing unusual, but really at low temperatures, they curved down and it became more like a power law dependence. So what's important here is really linear temperature dependence is rather a high temperature effect. And really what you can also do with these curves, you can plot them on a log scale. And you can really show that really there is a T to the 4 temperature dependence at low temperatures, which then transitions to a linear temperature dependence in high. And so this behavior is really nothing else which you can find in textbooks on sort of electron-phonon interaction in normal metals. And what's important to know here is that in normal metals, the Debye temperature usually defines your energy scale for electron-phonon interaction. And this Debye temperature is usually what is defining sort of the transition point between this power law low temperature behavior and this linear high temperature behavior. So in graphene, what's special is that we really don't observe a Debye temperature, but we observe a reduced Debye temperature, the so-called Bloch-Ruhnhausen temperature. And this is really just due to the fact that quasi-elastic scattering can only happen on the Fermi surface. So only phonons that have low enough energy to scatter electrons on the Fermi surface can actually scatter them. So there are very much fewer amount of electron and scattering processes in graphene that are allowed because of these energy conservation processes. So this Bloch-Ruhnhausen temperature is basically given here. And this is really proportional to the size of the Fermi surface, and it's then also directly proportional to the carrier density of the material. Okay, so what we then really realized is that in principle, if you follow this analogy, a lot of things can be explained by twisted bilayer graphene. So again, twisted bilayer graphene have a very low carrier density. So in principle, the Fermi surface can be very small, and therefore the Bloch-Ruhnhausen temperature can be very small. So that would basically push the linear temperature dependence to lower temperatures. And at the same time, also because the Fermi velocity in twisted bilayer graphene is very small as well, this makes this term extremely big, and this explains the high slope and the Planckian scattering rates in the material. However, this model, no matter how you turn it, we were not able to explain a Bloch-Ruhnhausen temperature which was below 1 Kelvin. So all of this physics can only be true above 1 Kelvin. Okay, so this brings me now to twisted bilayer graphene. So we wanted to really study the phase space where this electron-phonon picture just cannot hold true, and we decided to measure our devices in the millikelvin temperature regime and to see what happens really at 30 millikelvin, way below like what can be explained by electron-phonon interactions. And for this, we also used some of the devices which we made before for a different paper. So we basically made a certain set of devices which had a slightly smaller twist angle and which had a very close screening gate. to the graphene in order to make the correlated insulators a little bit weaker. And this device is shown here. And as you can see, so the correlated insulators in this device are not very strongly pronounced. So that allowed us really to cool the devices down to millikelvin temperature and follow that strange metal behavior down to these temperatures without being interrupted by any correlated insulators. Okay, so long story short, so this are the results. So again, we took a lot of curves where we measure resistance as a function of temperature for the different fillings. And indeed, in the center of the band, for filling factor -2 or so, we observe really linear temperature dependence from around 20 Kelvin to down to 40 millikelvin. And this is better seen on this log-log plot again, where really we can trace one of those curves and trace the linear temperature dependence from around 20 Kelvin to around 40 millikelvin. So this is really a linear temperature dependence of 3 orders of magnitude. Really, if you look at where sort of we would expect the electron phonon picture to hold, is really only for temperatures above here. So everything which is below here would not be explained by an electron phonon interaction. And we really conclude that these lines here are much more similar to what people observe for strange metals rather than what we can explain easily by electron phonon interaction. One thing is also important, close to the edges of the band, we again recovered this kind of T-square dependence. So again, closer to the edges of the band, where correlations are not supposed to be that strong anymore, we recovered the sort of Fermi liquid-like behavior. And this was really good to see that, because at least this gave us assurance that this sort of Fermi liquid behavior we can also see in these devices. So to give a little bit more assurance to us, we also measured magneto resistance. We really saw linear magneto resistance also being the strongest close to the center of the band. And we saw a d-square dependence closer to the band edges. And really the density ranges of the magnetic field linear dependence and the temperature dependence really matched nicely as well. Furthermore, this linear temperature dependence, it is really also survives at exactly the same temperatures as a linear temperature dependence. So at around 50 Kelvin, this sort of linear magneto resistance was gone. So again, the temperature scales here and the magnetic scales and the density scales of this behavior really all seem to match up. And of course, also we were able to sort of from Shubnikov-de-Haas oscillations, we were able to extract the effective mass and really extract the scattering rates and compare them to our data. And really all of these strange metal curves, they also have finely limited scattering rates. So with this, let me then conclude. One of the things I think which were also interesting is that, of course, having superconductivity in this device, it was interesting to see what is the parent state of the superconductor. And of course, you can kill a superconductor by applying a small magnetic field. So this is what we did here. So we killed the superconductor here by applying 300 millitesla. And at these 300 millitesla, we were still measuring this linear temperature dependence of the resistance. So basically, which means that the strange metal phase is also the parent state of the superconductor. Or in other words, the superconductivity state is born out of this metallic state, which also has this linear temperature and linear magneto resistance. And so if this really, this is the phase diagram which we were able to draw. So really, this is sort of, again, the phase as a function of the filling. And really close to the band edges, we observed the liquid behavior. Then we observed a broad dome of strange metal behavior. And basically buried in the strange metal, we observed the superconducting dome. Okay, and with this, yeah, I'm going to be done. I want to thank my group for the work, and I want to thank you for your attention.
Thank you so much for a really interesting set of talks. Yeah, I think we'll start with questions and then we're gonna go ahead.
Can you show this log plot again? Yes, here. So you see that for that temperature range, it could be the acoustic reason, right? But the other one, it's definitely strange. Is there any way to distinguish between these two linear
I mean, okay, so I mean, my understanding is that if a slope continues without interruption like that, then and you can exclude the lower part by electron phonon, then you can probably exclude the whole part by electron phonon. That would be my understanding. Yeah.
And but also I mean, it's a little bit difficult to see, but if that line is a lighter ray, right? Because there are a lot of points from the the other rays, darker rays, which overlaps the lighter rays. So I'm saying that in the range which is supposed to be on the string metal, data are a little more fluctuating.
Fluctuating.
Yeah, it's a little bit. I mean, the fit's very nice after that temperature. It's almost perfect, right?
Yeah.
But if you go down that temperature, it seems that there are some more data points which are a little off.
Which ones? Like this here?
Yeah. Or and also
this is a superconductor. This is a superconductor. This one is a superconductor. So also like, look, I mean, I think.
So I mean, you see, there are a lot of darker reds, or I don't know, more red, what you call it, which is exactly in the same line as the one that you fit, right?
Yeah.
This is
No, exactly. I mean, okay, so you don't expect like 100% exact linearity. Also in the cuprates, you don't. I mean, also the pnictides, so you don't observe that.
So we're just trying to see if there is an actual distinction between these two. Acoustic version, purely a strength level.
Okay.
Question. 17B linear behavior is indeed a lot like the pnictides. Is there an associated quantum critical point here that we
right?
hypothesize?
Right. So basically, okay. So here, this -2. This is one of the correlated insulator states. This is where we observe a Fermi surface reset, and this is where, I mean, this is what I talked to the rest of the talk today about, right? So there's so if you want this can be a quantum critical point, but because we also have the -1 here and -3, there's also the Fermi surface resets going on there. So in principle, I mean, and originally we called that paper actually quantum critical continuum, because we maybe have more than one critical point, right? In principle, you could think that we have 3 critical points here, right?
It seemed like what you were calling the parent state is somehow in between.
Yeah. Okay. Yeah. But I mean, so exactly. So I mean, this is right. I mean, this one of those states. This is where we observe these phase transitions, right? And we know that some of these phase transitions are magnetic. And again, that kind of again, if you want to play that analogy to quantum critical point, this is all about spin fluctuations and things like that, right? So, but again, it's maybe too early to make arguments like that, right? Yeah. So far, I really want to emphasize this is all phenomenology, right? This is really, we don't know the mechanism of what's going on here.
So continuing to the last question. So in the log plot, you show that the power law dependence is like from T power law 1 to, you also show like T power law 1.9.
Right.
So in between, is there any transition for power number?
Yeah. So that's a good question. So I mean, you probably exactly. It's probably easier to look at these lines here, right? So they gradually become linear, right? So probably you can fit many of these intermediate curves like a T plus T squared, something like that. That's also what's done in the cuprates and the pnictides, right? Right. So it's a gradual transition. It's not like, and also this is, I mean, probably this is what we wanted to say in that plot. So I think if you go make a line cut here, you have a combination of T squared and linear, right?
Okay, so you mean that you can just do some like easy calculation with class power law T power law 1 plus T power law 2.
Right, something like that. Yeah.
But it's not some number that in between, just T power law like 1.5 or T power law.
No, well, I mean, you know, so again, this is you know how one can, if one plays enough of power laws, one can probably fit everything,
Yeah,
right?
Yeah.
So that's in origin, you can go to the monomial function, and it fits you everything you want, right?
Yeah, exactly.
So I think right. We haven't tried. We haven't tried it, whether we can fit it with 1.5 or so. But it doesn't look like it. You see, like it's they all kind of become linear-ish towards slightly higher temperature, right? So it's yeah.
I have a question. So this picture is interaction correlation free. So if you take this formula of electron photon scattering that you took from your thesis,
Yeah.
doesn't include interaction.
It's no interactions. Yeah, it's just pure simple textbook electron photon interaction. Yeah.
So what do you think how it will change if you include the correlation or interaction?
Sorry?
So how is it going to change if you include interaction or correlation?
Okay, so right. So okay, so I want to let me just say what we did. So when we started looking at the data set, we were not after strange metal. We were really, so we were talking to many people. We were first trying to fit it with Umkopf scattering because of the moray, we have electron photon is probably also governed by Umkopf scattering phenomena. Then, of course, once you have an electron photon picture, you can also introduce some impurity, some electron impurity phonon scattering processes. Maybe you can throw in interactions on that. So you can make it as complicated as you wanted. And of course, we didn't. I mean, so what I can say is we couldn't fit it with the normal single layer electron acoustic phonon interaction. We couldn't fit it with Umkopf scattering for twisted Bilayer graphene. But then, of course, I cannot exclude any other theory which would come across. What I can so say is I think my personal strongest belief about the strange metal here is also, of course, the linear magnetoresistance. So I think whatever electron phonon mechanism you try to assume here, probably you can find something which fits the linear temperature dependence, but at the same time that it fits the magnetoresistance, that's a little bit less clear. So electron phonon should not couple to magnetic field so much, right? So the combination of those observables is something which intrigued me personally the most. Yeah.
I have a question regarding the superconducting junctions, specifically the SCS junctions. Have you considered any other geometries, or if that's possible to configure?
Yeah. So I mean, right. So basically, this is of course the simplest possible geometry. This is just the first geometry we did. Of course, you can make these line cuts at an angle. I mean, of course, it would be also interesting how this is all tied to the crystallographic orientation of the moray, right? Of course, there's also people, and including us, we're trying to make, we try to proximatize it with known S-wave superconductors, because one of the questions also interpreting this is what is the nature of the superconducting state? Of course, we don't know that, right? So yeah, of course, I mean, this is, you can probably do everything, quantum junction splits, like these current loops, what are they called? Like these magnetic, these sort of forks that people do to measure phase dependencies, where they send magnetic flux through it, right? So you can do all of this with that system as well. Yeah.
We have a few questions.
Yeah. Okay, this is one. There we go. We've got a bunch of online questions, so I'm going to try to synthesize things as best I can. Going back to the superconductor, what can you extract from the differential conductance curve, BCS versus BKT type behavior?
Okay, so it's just basically, so a BCS superconductor should scale as a I to the third here. Of course, this is not exactly proof that it's BKT, but because it's also two-dimensional and we know that, we strongly assume it's BKT. I actually haven't measured. I have actually never measured a three-dimensional superconductor, so probably everything I ever did was BKT. So I don't know. But basically, in the BCS, it would be much sharper transition as far as I understand. It was not I to the third; it would be much sharper, right?
Yeah, right. Okay. And the next question is about the temperature behavior of the thermal conductivity for a spatially heterogeneous S-wave superconductor.
Can you comment on how that could be?
Spatially heterogeneous.
Yeah, like a disordered aspect superconductor, I would imagine.
Okay. Then it has to be super disordered that somehow right. So I mean, one thing what I know is that S-wave superconductors are very stable under disorder, and D-wave superconductor, the superconductivity breaks down if you introduce too much of disorder. But in S-wave, yeah, I'm a little bit puzzled. Yeah.
Okay, and moving on to the thermal conductivity, can you learn more about the superconducting state by simultaneously recording the thermal Hall conductivity in addition to your conductance data?
Good idea. Yeah, probably we should do that. Yeah.
All right, nice job.
Yeah.
Okay, in 2D, is there a correspondence between the strange metal and the anomalous boson fluid at low temperatures?
I don't know what an anomalous boson fluid is.
Not quite sure.
I guess the saturation of the system behind so the anomalous net, so which if you cool down with temperature, low temperature, the resistance will saturate. Possibly like in some Indian tin system, they can observe that the resistance with applying some small magnetic field, and then the resistance will saturate at some number, but not dropping to zero.
Okay.
It's saturated, maybe starting from 1 Kelvin temperature. It keeps saturating down to min Kelvin. So there was some theoretical proposal and saying that this might be a false metal.
Okay.
And so the experimental observation would just be a saturation for resistance.
Oh, so basically there are Cooper pairs formed, but
Yeah,
they're
yeah.
not coherent somehow.
Exactly.
Okay, this, yeah. I mean, yeah, I've seen a lot of talk. I've heard a lot of talk in this context. I mean, we don't have any evidence for this yet that there is a boson metal.
Yeah, I think on the theoretical end, we might call this like the ECS versus EC kind of crossover. You can tell me, Daniel, if that's what you're talking about. Okay, but more from Daniel.
Daniel
for the
who?
strange metals. Yeah, he's asking lots of
Daniel who?
questions. Daniel S. Sanchez. I don't know if
Okay.
anyone knows him. Doing great, Daniel. Does the T linear behavior persist up to and beyond the single electron resistance quantum at a temperature is increased?
Do you have an answer to that?
Last one from there.
Okay, all right.
Does the superconductor strange metal transition have any characteristic critical exponent? And I might say sort of more broadly as instrumentalists, what kind of signatures might you expect going between these two finite temperature bases?
Oh shit! Like critical exponent in the.
Maybe there encounters a phase transition between.
Wait a second. So let's try to understand this one. So critical exponent in this measurement here.
And like go back to your phase diagram.
So this was this guy here, right? This guy here, right?
Yeah, or I guess in the plot on the left, right? There's a departure from the superconductor into the strange metal. I wonder if there's anything you can characterize that.
So wait a second. So there's one curve, the red curve, which is the superconductor.
Yeah, that's right.
And then there is one curve where the superconductor is completely gone, and it's a strange metal. But there's no crossover here.
But if you look right on the boundary, some critical field where these are competing. Is there anything?
Okay. So yeah, no, we need to look more careful on that. No, we haven't looked carefully on this transition.
Great. Okay, then I think let's thank Professor Efetov again for
thanks.
ruling around. After this, everybody, we have some very excellent posters.